Yo voy a... Bueno, sí, yo voy a terminar.
Hello, good afternoon. Welcome to this talk. It is an honor for me to share with you all these introductory words for today's invited speaker, Roberto Miatello, distinguished professor from the School of Mathematics, Astronomy, and Physics in the National University of Córdoba, Argentina, and also a senior associate member of the International Center for Theoretical Physics in Trieste. Roberto got his PhD at Rutgers University in, well, I'm not going to hint your age, so let's say a few years ago, under the advice of Nolan Wallach. From the very beginning and throughout his career, he has made important contributions to the understanding of the geometry of homogeneous spaces under bundles, usually combining analytic and algebraic tools. Roberto's work has also provided us with a clearer and deeper understanding of the perhaps by now classical relationship between the spectrum of the Laplacian and topological and geometrical properties of the manifold in question. He's definitely the person to ask about this subject, and he's also the person to ask if you want to know something about flat space forms. Of course, he has received several distinctions and awards for his research work. After 8 years at Rutgers, he decided to go back to his native Córdoba, and we all remember, well, he became a driving force, founder and driving force of what is now a very fine and renowned Department of Geometry in Córdoba. We all remember him as a very generous person, trying to advance the opportunities for international exposure of his younger colleagues and other colleagues in Córdoba, even in very difficult times, economical times for Argentina. So it is really a pleasure and an honor for me to introduce his invited address today. Welcome.
Thank you very much, first of all, for the invitation to give this talk and for the introduction. I'm very pleased to be in Guanajuato again. So I'm going to speak about a subject that could be called, described as spectral geometry, that has to do with the relationship between the spectrum of the Laplacian on a compact Riemannian manifold and the geometry and topology of the manifold. So we, as a quick introduction to the subject, we have M, a compact Riemannian manifold, dimension n, and the Laplace operator on M, which is an elliptic second-order differential operator, which has a spectrum, which is a sequence of eigenvalues tending to infinity, non-negative eigenvalues, which only depends on the isometric class of M. We shall denote it by spec M. And also, we denote by spec P of M the sequence of eigenvalues of the Hodge-Laplace operator on P forms on M. The spectrum on functions, that is spec 0 of M, which is spec M, and spec P of M are connected to the geometry or topology of M. So one instance is that the multiplicity of eigenvalue 0 of delta P is the pth Betti number of the manifold. So it is a classical question to investigate how much of the geometry and topology of M can be recovered from the spectrum. So the study of of this connection was popularized by Mark Katz in an article in the Monthly in '66, where he raised the question, and that's the name of the article: can you hear the shape of a drum? That means, suppose you have two plane bounded domains. So that would be a drum which might have holes, okay, has a smooth boundary or not. And then if it sounds the same, the sound is given by the eigenvalues, by the frequencies of vibration of the drum. Two drums which sound the same, will they be isometric? So after quite a while, counterexamples were given by Caroline Gordon, David Webb, and Scott Wolpert in '91, which are non-convex domains with polygonal boundary. There are not yet counterexamples known with smooth boundary. I wish to say Caroline is sitting here. It's a pleasure and an honor to have her here. So suppose you ask about isospectral closed Riemannian manifolds, so no boundary and no bounds on the dimension. And suppose also the answer is negative, so it means Milnor was first to realize that Witt had constructed two 16-dimensional lattices which are not isometric, that is, there is no orthogonal transformation taking one to the other, but which have the same number of elements of a fixed length for each length. Well, later other people worked with tori, lowering the dimension. Gneser, for instance, and Kitaoka. And the lowest were found by lowest dimension was due to Sheeman in 1990 for n equal 4, and Conway Sloan found some infinite families using error-correcting codes. Sheeman proved in '97 that for n equal 3, there are none of these. For n equal 3, there are very nice compact flat manifolds, which are isospectral and geometrically very different. In general, we want to mention that if you have a lattice in Rn and you take the associated torus Rn mod lambda, then how do we construct eigenfunctions? It's rather simple. We take lambda star, the dual lattice, then we take fv of x, e to the 2 pi I v, inner product with x. This is a function on Rn. And then it is easy to see that it is an eigenfunction of the Laplacian with eigenvalue 4 pi square norm of v square. I mean, if you take n equal 1, then you see that if you differentiate twice, then you get minus 4 pi squared, and then v squared. We have to change the sign to get a positive Laplacian. And now the need to take v in lambda star is that we want the function to be invariant by translation by lambda. So then these functions easily are seen to span the L2 space. So we get a complete set of eigenfunctions. But on the other hand, if we think about it, we cannot still say the spectrum is known, even for the canonical lattice, unless we know for each number lambda how many v's there are of that norm square. So even for the canonical lattice, to find the spectrum means to be able to solve, to find the representation numbers of a quadratic form. So fortunately, it's easier to prove that two manifolds are isospectral than to find their spectrum. Okay? So sometimes it's possible to, I mean, like in the case of the Witz lattices, to prove isospectrality, and in that case, a nice tool for that is modular forms. Okay? When you have a certain you construct a modular form, and you know that the space of the dimension of that space is 1, and then you use the two lattices, and this helps you to prove isospectrality. So, since Mark Katz's question, there were lots of results on the subject. Apparently, I wrote the number of citations it has, more than 1,200. So, well, I singled out a few important results on this. There's a paper by Marie-France Vignerat, which was important, who was the first to construct hyperbolic 2 and 3 manifolds that are isospectral and not isometric. Then Caroline Gordon has done a lot of work on this. For instance, Caroline Gordon and Wilson, they constructed continuous isospectral families of solved manifolds. Also, the first examples of Riemannian manifolds isospectrum function not on one forms were constructed by her. And then an important step forward was given by Sunada, who gave a method to build many new examples. He gave a method where you take a manifolds and then two finite, in principle, at the beginning, finite subgroups of the isometric groups. And then the quotients are isospectral if you have a condition of conjugacy. If the groups are quasi-conjugate in a bigger group within the isometric group, then the quotients will be isospectral. And usually they will not be isometric, not even homeomorphic. Then a student of Caroline, Ruth Cornett, has done quite a bit on length isospectral manifolds. Then you have Aikida, who worked on isospectral length spaces. And then there is our group in Cordoba, I should mention. We have a variety of phenomena detected in Bieberberg manifolds. That means compact flat manifolds. So a rather difficult question is how to construct manifolds that are p isospectral for some values of p only. Okay, so what I want to do today is talk about recent joint work with Emilio Lauret and Juan Pablo Rossetti, where we study the p-spectra of manifolds for constant curvature space forms. And then we'll use group representations. So that means we'll connect the multiplicities of eigenvalues for the pth Laplacian, or the Laplacian on p forms, with multiplicities of certain representations of the isometric group. So the situation is we have X, which is a constant curvature space, is either the n sphere Rn or the hyperbolic n space, and then we write these spaces conveniently as G mod K, as symmetric spaces. So the full isometric group will be On plus 1. So Sn is On plus 1 mod On. Then Rn, in a fancy way, we can write it as On semi-direct with Rn, mod On. And then the hyperbolic n space is Lorentz group mod On. So the K is always the same. So the general setting is a homogeneous Riemannian manifold. Actually, it's a symmetric space where we have G is the full isometry group. K is a maximal compact subgroup. Gamma is a discrete co-compact subgroup of G acting on X without fixed points. So for X of constant curvature, gamma is a finite, so X mod gamma will be a spherical space form. They are classified in Joe Wolf's book, who pleasantly is here also today. And in the case of Rn, we have a Bieberbach group. So that means a crystallographic group which acts without fixed points on Rn. Or the same, it has no elements of finite order. And then gamma can be a hyperbolic group. That means it's a discrete co-compact subgroup of the Lorentz group which has no elements of finite order. Okay, so we now need to get into representation theory, and then it is a classical fact that if we divide by gamma, the quotient is compact, then we get a representation of G by acting translation on the right. Okay, and this is a unitary representation of G in all three cases, G compact or the other two cases, and then it is a classical fact that this representation decomposes as an infinite sum of unitary representations of G which have finite multiplicity. So this is a consequence of the spectral theorem of compact operators, basically. I think it's due to Gelfand et al., or the school of Gelfand. So each pi is a closed G-invariant irreducible subspace with finite multiplicity. So the multiplicities n gamma of pi are rather unknown in general. Okay. A case when they are known is in the case of spherical harmonics, but this is a very special case. So now we take a unitary representation of K, v tau, finite dimensional, and then we form the associated vector model over G mod K. So this is just taking the product G cross v tau under the action of K. K point GV is GK tau K minus 1 or tau KV. Okay, then we have a G-invariant inner product, we assume, and then we take the natural Laplace operator acting on sections. Now we form E tau mod gamma and X mod gamma, and then we have a vector bundle, and then we have a natural Laplace operator in that space, acting on sections on that space. Then this is connected with work of Pese, who considers a subspace of L2 G mod gamma, which is associated to tau, just takes into account all those representations which have something to do with tau, such that the representations of G such that the multiplicity, when you restrict the representation of G to K, the multiplicity is non-zero. So Pese defines two subgroups to be tau representation equivalent if the two spaces, those two spaces for gamma 1 and gamma 2 give equivalent representations. This means n gamma 1 pi and gamma 2 pi are the same for all pi, but only for all those pi on G hat tau. Of course, well, tau isospectral means that the spectra of the Laplace operators for gamma 1 tau and delta gamma 2 tau are the same. So these are operators acting on the vector bundle. So Pesce proves the following theorem. For every constant curvature space form for tau equal 1. He proves that x mod gamma 1 and x mod gamma 2 are isospectral functions if and only if the L2 spaces are representation equivalent. So what our goal now is to consider tau p, the p-stereo representations of ON, and then consider the same question. In which way, if isospectrality and representation equivalent are still the same. So what we shall do is explicitly give the multiplicities of it turns out that in one direction it's easy to see that if you have tau representation equivalence, then the manifolds are tau isospectral. The problem is the opposite. If you have isospectrality, then whether the representations will be the same. So what we shall do is give the multiplicities of eigenvalues expressed in terms of multiplicities of representations. And then, in case we can do it with one representation, then the Pesce's result will hold, and whenever not, we shall see that it doesn't hold. So we work with tau p. So is the representation of ON in the pth exterior product. Okay, with those particular representations. Of course, one could use any representation of ON, and I will say a bit about that also. So we will use a general approach that applies to all three cases, and then we show that Pesce works for any p in the spherical case. So for the sphere, things work. In the flat and hyperbolic cases, p isospectrality does not imply tau p equivalence, but we can give a generalization of Pesce's result. So we also compare with work of Ditark and Carlin Gordon, Joe Wolf, Pesce, Gornet McGowan. So I will state the theorems first, and then we'll say something about the proofs. So for the sphere, okay, so we start with the finite subgroup of ON plus 1 acting freely on an odd-dimensional sphere. So the dimension n is 2n minus 1, and then we take p between 0 and n. And then we define E sub p is the set of lambdas which have such an expression k squared plus k n minus 1 plus p minus 1 n minus p. And this for every k in n. And then we take E sub p union E sub p plus 1. It turns out that E sub p and E sub p plus 1 are disjoint sets. And then what we prove is that if you take lambda given by that expression, then d lambda, the multiplicity of the eigenvalue lambda for p forms for gamma, is given by the multiplicity of unique, well-determined representation. With highest weight, lambda kp, where lambda kp is of the form k epsilon 1 plus epsilon 2 plus epsilon p. K is either a natural number or a non-negative number in the case p is 0. The case p is 0 is the case of spherical harmonics. The k has a formula, I mean, it's uniquely determined, okay, by lambda, by that equation. We'll give it later. But what we see here is that the multiplicity, the spectrum determines the multiplicity of representations. So if two gammas have the same spectrum, the same p-spectrum, then the representations will be equivalent. So this is sort of the content of this result. So corollary, I is x mod gamma 1 and x mod gamma 2 are p-isospectral if and only if they are tau, the groups, the discrete groups are tau p equivalent. And then there is another consequence, is that if x mod gamma 1 and x mod gamma 2 are p minus 1 isospectral and p plus 1 isospectral, then they are p isospectral. If p equals n, then if they are n minus 1 isospectral and have the same nth Betti number, then they are n isospectral. Well, there are a number of results previous to this on the case of the sphere. We have Aikida. He has a remarkable paper which is probably not yet totally digested by many people. He constructed length spaces that are q isospectral in a segment from 0 to p, but not p plus 1 isospectral. And for that, he needs to take a large n. Okay? But he can do it for any p. So for any p, you want length spaces that will be a q isospectral for every q, or isospectral on q forms, for every q from 0 functions, 1 forms, 2 forms, up to p. And then not for p minus 1. So that's what he constructs. But n is large. Now then, by computer methods, Gornet-McGowan found a list of length spaces that are p isospectral for some scattered values of p. They are also, there will be tau p equivalent for these values of p only, okay? So you see that. But on the other hand, their list shows no simple holes in the set of values of p for which they can be p isospectral. And this is consistent with the result of 2i, that you say you cannot have a hole. If you have p minus 1 and p plus 1 isospectrality, then it will be in the middle as well. And then Joe Wolf has produced many examples of spherical space forms which are strongly isospectral. So isospectral on p forms for all p and for all natural operators, and by using Tsunada method, I think. So now for flat and hyperbolic cases. So then in the flat case, okay, we have a Birba group, a discrete co-compact subgroup of the isometry groups acting without fixed points on Rn. Now we take lambda translation lattice of gamma, we take the dual lattice, then we can give the multiplicity of an eigenvalue lambda as follows. So the multiplicity of 4 pi square norm v square for v in lambda star is given by, for 0 is the pth Betti number, and for lambda greater than 0 is the sum of two unitary reducible representations of the isometry group. So these two representations are infinite dimensional, they are induced representations. They are constructed by the Mackey machine. Okay? So for lambda positive, then the d lambda is a sum of two, multiplicity of two representations. We shall see that we cannot fix that. I mean, the d lambda does not determine the multiplicities and gamma individually. So finally, the last case, hyperbolic case, we have gamma, a discrete co-compact subgroup on Hn, now is a hyperbolic group, okay? And then we can express the multiplicities of eigenvalues, again, in terms of representation theory, of unitary representations of the Lorentz group. For lambda equals 0, okay, then we have a different situation for p, so the dimension is n. When n is even and p is half n, then the multiplicity is given by the multiplicity of the so-called discrete series representations. Actually, it's a sum of two, but this sum is irreducible, because notice that the group G is not connected. So all these groups are not connected. So even for the compact case, we have to take into account the two components, the two connected components. On is not connected. Okay, so there are some representations that are irreducible for SON. They will be irreducible for ON, but splits as a sum of two for SON. So this happens here. And we would not get the same results if we express the sphere as SON plus 1 divided by SON. So this is a valid expression, but we have to take the full isometry group. So we need to work with ON to be able to separate the multiplicities of the representation. So in this case, so these are some representations called Langlands quotients. So these are very peculiar representations that of SON1, and in this case, for p different from n over 2, for the eigenvalue 0, we have this expression. So if lambda is positive, then the d lambda is the multiplicity is the sum of multiplicities of principal series representations. With the right, if you fix lambda, then you need here the right parameters. Okay. So these are specific unitary reducible representations of G. So in the proofs, we use the description of the unitary duals of G in terms of induced representations. Okay, so it's a good exercise in representation theory to this. So generically, there are two irreducible representations contributing to the multiplicity of an eigenvalue, and these multiplicities are linked to each other for p and p plus 1. So this is a generalization of Pesce's result. So if you have a simply connected symmetric space of constant non-positive curvature, where G is the full isometry group of X, and gamma 1 and gamma 2 are two discrete co-compact subgroups of G acting without fixed points on X, then for each P between 0 and n, X mod gamma 1 and X mod gamma 2 are Q isospectral for every Q between 0 and P, if and only if gamma 1 and gamma 2 are tau Q equivalent for every Q between 0 and P. Okay? So this is, it doesn't say that if they are Q isospectral, they will be tau Q equivalent, but if you have a segment, then the same segment holds for the other. Well, then we derive consequences. If you have manifolds that are tau 1 equivalent, then the manifolds are 0 and 1 isospectral. We give an example of two 4-dimensional compact flat manifolds that are 1 isospectral and 3 isospectral, but not 0 and 2 isospectral. So then they are not tau equivalent. They are not tau p equivalent for no p. So this is a drastic counterexample in the sense that you can have some isospectrality for, if you have 4 dimensions. So these manifolds will be T4 divided by the Klein group, Z2 cross Z2. So they are very easy manifolds. Okay? They are compact flat manifolds which have holonomic group Z2 cross Z2. And then they turn out to be 1 and 3 isospectral, but they are not 0, 2, and 4 isospectral. So they cannot be equivalent for tau 0, tau 1, tau 2, tau 3, tau 4, for none of them. Then another consequence is that if 2 subgroups are type tau p plus 1 equivalent and they are p isospectral, then they will be tau p equivalent. So there are several. Well, another example is a funny example. We can give flat 8 manifolds. That means T8 acted on by a group Z2 to the cube, or something very simple, that turn out to be p isospectral for 1, 2, 3, 5, 6, 7. So they are very isospectral. They are not isospectral for 0, 4, 8. So it turns out, as a consequence of the results, that the groups cannot be tau p equivalent for any. Okay? So that's it's a drastic sort of difference with what happens for p equals 0. Okay, the Pesce's result. So here, a lot of isospectrality does not imply tau p equivalence. So if we had 0, 1, 2, 3, then we would have 0, 1, 2, 3 tau p equivalence. But we don't have 0, so if we don't have a full segment starting from 0, or a full segment going up to n, then we cannot conclude that. Well, the hyperbolic case, we don't have examples because they are very hard to construct, but they should exist. I mean, there's no reason why the multiplicities, I mean, if the multiplicities are expressed as a sum of 2 multiplicities of representations, then there is no reason to expect that one multiplicity will determine the. Okay, one of the main tools is this formula, which is rather the main tool is that if you look at the multiplicity of the eigenvalue of this operator, then this gets expressed in terms of the multiplicities of the representations and of the appearance of the multiplicity of tau in the restriction of h pi to k, provided we restrict ourselves to those unitary representations of G that have infinitesimal character equal to lambda. So this is infinitesimal character. So this is a basic principle that is rather and this is a sketch of proof, but the idea is rather, you see, if we take basically here, if we have this space, and then it turns out that the the Laplacian on the bundle is given essentially by the action of the Casimir element in the universal enveloping algebra of the group, and the Casimir element acts by a scalar on each irreducible representation. Okay? So if we take this whole space, we have just to take those, and we fix lambda, then we have to single out those representations which have infinitesimal character compatibly with lambda. But then, if we take all of the space, then we have an infinite dimensional eigenspace, but we have to take only those which involve that bundle. Okay, the bundle is given by tau. Okay, so we have to take the k invariants in this space, and then this is that, just that. So this is a formula which is, but then you see what we have to do. I mean, the task is now we have to determine the infinitesimal character of all irreducible representations of G, of the unitary representations of G, and then we have to use the multiplicity of tau in those representations in each of the cases. So it involves representation theory of compact groups, of semi-simple groups, and of a semi-direct product. So for compact groups, we have to use the highest weight theory and the detail of the fact that the group is not connected, so the highest weight does not determine fully the representation. So then so an irreducible representation, okay, then we need some branching theorems. So we need to know how tau p, the tau p representation, restricts to ON minus 1. So this is rather easy. So it decomposes as a sum of two irreducible representations that are essentially is the p exterior representation and the p minus 1 exterior representation in one dimension less. And this is the same proof when you want to prove that a combinatorial number np, okay, is n minus 1p plus n minus 1p minus 1. When you separate the last vector, and then it's the same. So this is the same, but this plays a role in the proofs. That's the reason why we get two constituents all the time. And then we have to take the highest weights that occur and then we determine those representations G hat of ON plus 1 that contain tau p. So this has just to do with determine the right highest weight. Tau p, notice that tau p has weight, highest weight, all ones and then zeros. So the branching requires that the highest weight of the representation of ON plus 1 has to restrict, has to be of this form. And then we can prove the theorem. We write the eigenvalue in this way. This is known. This is rho. So rho is a standard object of Lie algebras. So it's have the sum of the positive roots. So for the case p equals 0 is the case of spherical harmonics, which is well known. But still you see we that the multiplicity is the multiplicity of the eigenvalue is given this multiplicity of the representation. So here is a highest weight, a multiple of epsilon 1, and this is a sign. The sign has to do with the two components of the ON. And then in the other case, then we have to do the homework, okay? I mean, do the calculations and determine k lambda, and we see that for each lambda, there is a unique k lambda which solves the problem. So then, as a consequence, and finally, we have to check that the two eigenvalues for p and p plus 1, there can be no coincidence there. So this is a calculation, and then we arrive at d lambda tau p equals n gamma. Okay, so then, so we get the first theorem that that the multiplicity of eigenvalues determine the multiplicity of the representations, and then we get also the result on the holes. Then we can generalize this. So we can prove the same result for other representations than tau p. So we do it for one. So the question is whether tau isospectrality implies tau representation equivalence in other cases, for other taus. You see, these tau p's have a very nice highest weight. It's a highest weight 1, 0. So it's a very simple one, so for all p's. Okay, now we use another type highest weight, and then suppose we take all coefficients between 0 and 2 decreasing in this way, then tau isospectrality implies tau equivalence. So then what we have to see is that different representations here have different Casimir eigenvalues. So this is it involves a calculation, an argument that I can show just this. And eventually then we arrive at that. So the conclusion is that we get that for other taus, then the result is true in the spherical case, but this is previous work. But this remark, you see, is not true in general that for any tau, any highest weight you pick, then only one representation will contribute. So it would seem that the result is not true in general. For instance, for this highest weight, okay, then we get that this eigenvalue is equal. So this eigenspace is the sum of two representations, so it's not irreducible. So then we cannot conclude same. Well, then there is we can do some conclusion about closed and co-closed forms. So spherical space forms were isospectral on closed forms or co-closed forms. So this was work of Gornet-McGowan. They found many examples. So they introduced the notion of half isospectrality, so meaning isospectrality with respect to delta restricted to closed or co-closed forms. So they showed that there are examples of half have isospectral length spaces. So in the flat case, we can give well, we have a formulation. Okay. So. Well, now, time permitting, I will do the flat case, but I think I already explained it. Well, I can do it quickly. We have to use the Mackey machine to identify the unitary reducible representation. So these are, they look like this, except for a few which are finite dimensional. So this is what the induced representation is a completion of the space of functions that transform according to a semi-direct product of On with Rn. And then we get that this representation is irreducible, and every unitary representation of G is unitary equivalent to one of these forms, with a few exceptions, which I find dimensional, which are the representations of which come from On. So this is so we have a description with a unitary dual, and then we get a description of the part of the unitary dual that involves tau p. And again, the inducing representations have to involve the representations that occur in the restriction of tau p to On. So tau p is a representation of On plus 1, this is a representation of On. And then, well, we have the eigenvalue of the Laplacian will be given by this operator of the universal enveloping algebra. And with that, it's not hard to get at this. And then some consequences. And then we arrive at the proof of the theorem in the flat case. So I guess I will stop here. Thank you very much.
Are there any questions? Yes.
These two striking examples of the flat four-dimensional and eight-dimensional. These two striking examples of the four-dimensional and the eight-dimensional flat.
Yes.
Yeah. So were those constructed somehow using the numbers or partitions?
It turns out that we know. You see, the thing with the flat case is that we have very explicit formulas for the multiplicities, for the multiplicity of eigenvalues on P forms. So it involves traces and it involves a certain sum here, which is, this is all sort of, you have the group, and then you can express the multiplicity of an eigenvalue in terms of traces. You see, the element of the group has a rotation part and a translation part, and yet you can express in terms of B and big B and small capital B and lowercase b, you can express the multiplicities. Okay, so then there are two ways we use this. So if we want to prove that two manifolds are not isospectral, then we have to show that in one or another, an eigenvalue has different multiplicity. So we have to use the formula. and compute. Usually that is to show when the manifolds are not isospectral on functions. So there are lots of examples of manifolds which are isospectral on forms, but not on functions. Now, how we get at that? Well, the reason is that the nice thing is that the trace P, the trace, is zero, often, sometimes, okay? So this is a phenomenon that is called, it has to do with zeros of Krautchuk polynomials, of polynomials in a finite interval of integers, okay? And then when this is zero, then unexpectedly, two manifolds that are not isospectral on functions, they are very different. But still, if trace P, trace 1 or trace 2 is zero, then they can be isospectral on one forms or on two forms. So then you can get isospectrality in that way. And then, for instance, here. So here these are one isospectral and not zero isospectral is because the trace is zero. The one trace is zero. But if you compute the eigenvalue, the lowest eigenvalue is different. Here is you compute it and you get 2 and 3. So they are not isospectral on functions, but they are isospectral on one forms. And then there is the curious example, which was, that is due to Rossetti, which he's the one who gets this. This is a curious example. Two 8-dimensional flat manifolds, P isospectral for every P, but not for 0 for 8. The corresponding Weber groups cannot be tau P equivalent for any P. So this is an 8 torus divided by Z4 acting freely. So these are the elements. Oh, sorry. So the thing is that this is a rotation vector. The rotation is a matrix. It's just a matrix, zeros and then 1 minus 1. It's a matrix of order 4. And this 1/4 means is a translation E5 over 4. It's a translation. You see, all these are sort of degenerate Klein bottles. It's just for higher dimensions. So this is the thing one has to think. A Klein bottle, you add a translation vector divided by 2, half a translation vector, right? Well, and this is what happens here. And then, well, this is the square and the cube, and, well, gamma to the 4th will be the identity, okay? Well, will be a translation, actually. It cannot be the identity because then there will be torsion. So it will be a translation vector. But, for instance, we use a multiplicity formula, you see, to compare the spectra. And so one isospectral is because the traces are 0, 1, 2, 3, okay? They are not 0 isospectral because the multiplicities are different. But then the 4 isospectrality, we have to still to compute it, and then we have an eigenvalue. You have these two numbers are different, so they are not isospectral on 4 forms. So everything is rather elementary at this level, but you get nice examples.
Any other question? Well, I'm sure that Roberto will be glad to answer your questions during coffee breaks. Thank you, Roberto.
Sí, bueno, disculpe. Creo que